Limit laws. We want to know limit laws because limits are going to be related to derivatives. Whatever applies here will apply to derivatives also. So when the time comes for derivatives, I'll kind of skim through the stuff because everything that applies and holds true here will also hold true with derivatives because derivatives are directly related to limit laws. Suppose we have two functions, f of x and g of x, and let's say there's some constant. By constant, I mean a number. So if the limit exists, which we are going to assume at a point A, so we are evaluating the limit of the function at A, and I want to evaluate it for the constant C. So do we see any x in this C? No. So do you believe that this limit would affect that constant? Because limits are applied only for x, and there is no x, so the answer would simply be C. So limit of a constant is a constant, because there are no x's there. Limit x approaches A, f of x plus or minus g of x. Limits exist, and of course f of x is a function of x, g of x is a function of x. So this limit will be applied to f of x as well as g of x. So we will simply distribute the limit like we do with simple algebra. This limit simply went in and it gets applied to each of those functions. Anytime when we add and subtract, limits are easy to evaluate. Would you like to fancy a guess as to what that would be? Just multiply the limits. Would you like to guess that?
Dividing.
Divide the limits. But we've got to be cautious for a couple of reasons. One, that limit, when we evaluate it, cannot be zero. Because then you'd have divide by zero. G of x cannot be zero. Later on, there's a thing called indeterminate forms, where when you apply the limit, you get 0 over 0, and that is not 0. So there is a rule to deal with it. We'll see if we can get to that. let's see if you can put 2 and 2 together. Or to be precise, A and C together. And come up with
Just multiplying C and f of x.
multiplying C with the limit. So I'm going to apply the limit for x, yes, or f of x, right? What do we know about C? C is a constant. So this limit is not going to affect that constant. So whether I apply this limit to C or not, C is going to be C. So I can pull that number out. And write it that way. So if it is a constant, if you have a constant, you can pull it out of the limit. Again, all of these properties will hold true for derivatives. Are we good so far? Yes.
I just don't understand it. I don't know if that makes sense, but
Well, got to be specific.
like, how do you get E? Like the whole part of E?
All parts of D,
E.
E. Yes. Now, what is the constant in that expression?
2x.
2. What is the function in that expression? X. So when I apply this limit, it's not going to do anything to that 2. So I'm just going to pull that 2 up. And apply the limit only to x. Now, no problems with x. So if x approaches 2, what is the value of x? 2. 2. Does that make sense?
Yeah.
Okay.
That law, does it apply with like quotient rule?
Come again?
Quotient rule, like when we go into derivatives and then we do like quotient rule, where it's like, on my teacher, like first times second prime. That's what that is for?
So that would come here. Quotient rule is not big.
Oh, okay.
Because if you have a constant, this is just, pulling a constant out of the derivative.
Yeah, that's what I'm saying, like saying, like that is like quotient
Yeah.
rule, okay.
So this is a quotient, this one.
But why is that like, so like you have like, if you have like two things and you want to find, I forgot the thing, so you would like take like the first, and then you have to multiply it by the prime, which is the derivative, and then you have to go, then the first prime and then the second, but why? Why do you do that?
So it goes back to the way we apply limits. When I do the derivative or quotient rule, I'll explain as to why. When you take the derivative of u over b, you get that formula that you're talking about. So there is a process, and it is because of that process we get that rule. Same with product rule also. But just be patient until we get there. So put this down. If n is positive, any thoughts as to what we can do here? Not in fraction. Like using all the things that we did so far.
Take the limit of the function, take the limit of the function and then,
just move this inside and then take the power. So. Good. Any thoughts? Just move it into the radical. Good. That leaves us with one. Any guesses?
Put the n.
Oh.
You put the n in the front.
That's there, that's a very no.
Oh,
I just want to know the limits. X is approaching A, I want to know the limits of X raised n.
do the limit of x approaching a of x, and then you square it, or you raise it to the x one.
Okay, so. Josh,
Lewis.
Lucas,
Lewis.
it's all good. So Lucas says we could just move it to X, then raise it to the power. Oh, it's not Lucas, it's Lewis. So limit X approaches A of X is A. So it's just A raised n.
And why is it for F and G? Why are you able to move it just into that spot? Is it the same reason kind of with H, based on how the limit approaches?
Yes.
or-
But it's based on the definition of limits. So just like, as long as this function is proper, there are reasons or there are explanations as to what proper means for a function. It's called regularity of the function. So if this is proper, then we can simply move the limit inside. Good.
What makes F and H different? Is it just because it says F of X and now it says
Now, where is this H coming from?
Pardon?
Where is the H coming from?
H, like F and H?
Oh, you're talking about these?
Yeah,
Oh, I see. Doesn't make any difference, they're one and the same.
okay.
But we have two functions, f of x and g of x. Now I'm going to tell you that f of x is less than or equal to the part is trivial. F of x is less than g of x for all x's in its domain. If that is the case, what would or how would the limits of each of them be related? Now, before I write that, let me ask you. So the domain of both functions, a to b, correct. Now, let's pick a point right in the middle. I don't want to confuse with this A, the A over there, and this one, so I'll call it x1, x2. Good. Now, I pick a point, A in this B. You tell me where do you want me to put that point? Right in the middle, okay. A. As we approach I'll give them numbers so that you can understand better. As I approach A from the left, from the right, what is the limit of the function g of x? 4. What is the limit of the function f of x? 5. If I move this point over here, do you believe that the limit of g of x will be less than f of x? 4 is less than 5, correct? Let me move over here instead. Some of the points, C, so as we approach A from either side, we got the limit of g of x to be 4, limit of f of x to be 5, and we agreed 4 is less than 5. Has to be. Now I pick another point C. I'm going to approach C from either side. What is the limit of C for the function g? 3. F. 4.5. Is 3 less than 4.5?
Yeah.
Yes. If I move it to another point, D, do you believe the limit at D for g of x will be less than the limit at D for f of x? Yes. So if this condition is satisfied, in other words, f of x is, I want to stick with that picture over here, so it has to be greater than or equal to, sorry about that. Of course, I could have changed the f there, but so if f of x is bigger than g of x in its entire domain, then no matter what point you pick between x1 and x2, every point will have a limit for f of x that is bigger than the limit for g of x. Do we agree? Okay. That must be true. The moment people see the word theorem, they get freaked out. Nothing to get freaked out. Nothing to be afraid. Here, if you understand the concept, you know, the theorem is easy. Should we use the same picture? No. Let's use a different one. Some people like to call it pinching theorem also, they're all the same. So what does the theorem say? Very simple. Suppose I have three functions. And what we know here is at that point A, h of x is stuck right in the middle between f of x and g of x, correct? And it is stuck in a way that it's really, really squeezed tight. Do we agree? So, it's really pinching at that point. So I would have this condition that g of x is less than or equal to h of x, which is less than or equal to f of x. Do we agree? So g is less than h, which is less than that at a at that point. So let's say at x is equal to a. Clear so far? So do we understand as to why we call it squeeze? Do we understand as to why we call it pinch? Do we understand as to why we call it sandwich? Right? Love one, love two, male. I meant to take slice one, slice two, male. Let's see. If that is the case, I'm going to call the limit of g of x and f of x to be 2. So go ahead,
Well, that should be 2.
do something.
I mean.
So it has to be 2, right?
I was gonna say, if it's in between g of x and f of x, and they're both 2, then it has to be 2.
Exactly. So they are getting really, really close over here. And I'm saying there is this another function that's stuck right in the middle. And I know that this is approaching 2, that is approaching 2. Then whatever that is stuck in the middle should have limits of 2. Correct. So that limit will be 2. You can replace 2 by c to generalize it, and that's what we call the squeeze, sandwich, or pinching theorem. Now, you will use this in this class when you do homework, in this section. But would you use it in life? Probably not, unless you become like a mathematician, statistician, or a physicist, one of those. Because there are certain functions where you will not be able to find a limit directly. In which case, we will pick functions that are close to the function of interest. And if we find their limits, and if we knew the function that we can't find the limit for stuck right in the middle, we can easily find this limit. So that makes sense. So past this class, unless you get into theoretical stuff, this is not important to you, right? So even when we get to derivatives and such, we probably would, we're not going to use Weierstrass theorem. But when you evaluate limits in this section, then don't forget. How could we forget a sandwich? Lunchtime. Do we see two functions? What are they?
Squared plus one.
X squared plus one. The other one, x plus one whole squared. They are in product, do we agree? So what does the law say, the limit law? It simply states find the limits of the first one, find the limits of the second one, multiply them together, right? So do you think x squared plus one will have any issues at that point too? Is there a break, jump, infinite discontinuity? None. So if none of those happen, the chances are the limit is going to exist. So you just plug in the value directly, you have 2 squared plus 1, you get 5. Good. Likewise, limit x approaches 2, x plus 1 squared, whole squared. Do you believe that this function would have any problems, jump, infinite, break, discontinuity here? No. So the limit is going to exist because we don't have any issues. So directly apply the limit to x, which would be two plus 1 squared, you get none. We're not done yet, right? We've got to multiply them together. So 5 times 9. What's it about? Good. Easy, right? So you don't have to, express or write each and every step in this class, because all we want to do is understand the concept of limits, how to apply limits, get the answer. So you don't have to write each and every step. So we want to apply the limit to that function, and get the answer. So give it a try. Use the properties and, what was it, A through I? A through H, you don't need the other two. Good. So when you do the homework, you don't have to, write each and every step. I can do this directly, but few questions to ask. Would any of these or both of these cause any problems at the point 1? That's very, very important. If something like that happens, then there is some trick that we've got to use. Would that function become a problem at 1? No. Would that become a problem at 1? No. So I can directly apply 1 as a limit to x. Yes. Apply 1 directly. So root 2 plus 2 cubed. Root 2 plus 8. Good. Did you have a question, Enzo?
Yeah, I was just gonna ask you, what would the problem be, and like if there was a problem?
We'll go there. Okay. Don't worry. Life is never fun unless you break something. I want you to give it a try. So we start to apply the limit, just root. Oh, crap. I should be able to- So sorry, or else the answer would be easy, right? So T, you should say something if I make a mistake. T approaches -1. Do you believe that we would have problems with any of those functions?
Yeah.
Both of them. Square root of -1, imaginary. Square root of -1, imaginary. We need a real number as a limit unless we're doing complex analysis. That's not what we're doing here. So we should try to get rid of that root somehow, right? If it is possible, then perhaps things would get easier. What is one way to get rid of a root? But I can't just square it, right?
Well, you can rationalize the bottom.
Oh, he's using fancy words. What's your name?
Geo,
Geo.
Yeah.
What do you mean rationalize?
can't you like, if it's -1t, can't you just do like a -1, square root -1t, and then you can cancel out the bottom? So it would be -1.
I love that.
Like you can, like when you do like tangent of like square root of 3 over 2, and then divided by 1/2, and then so you have to keep changing slips, so you have like a square root on the bottom, so to rationalize it, you also do a square root of 3. A square root of 3, square root of 3.
I see what he's saying. He's just not, phrasing it properly. Go ahead.
Multiply by the conjugate.
Multiply to divide by the conjugate. I forgot your name. What's your name?
James.
James. Wait, why do you sound so morose? James says we multiply and divide by conjugate. That's another fancy word. What do you mean by conjugate?
So you take the radical t minus 1 and then divide it by radical t minus 1, so you're multiplying by 1 essentially, but it gets rid of the radical.
So the conjugate of this is, oh, right in the next step. You see how I change that negative to a positive? Of course, I can't just arbitrarily multiply and leave things alone. Math doesn't work that way, so I multiply and divide by square root of t plus 1. So this is what we call the conjugate. The conjugate of that. Now, this process is used in a way, so that we can find a limit if things go awry, like it did here. How does it work? Well, by multiplying it by the conjugate, I have this expression, which is simply a minus b times a plus b. What is a minus b times a plus b? Times. A minus b times a plus b.
A minus b squared.
A minus b squared.
Right, plus b squared.
Let's go through every single option.
Isn't it a squared minus AB?
Go ahead.
I was gonna say plus
Keep going.
minus B squared.
Close. If you FOIL this, you will get a squared minus b squared. It's a standard identity. So in this case, a is root t, b is 1. So a squared so root t squared minus b squared divided by root t plus 1 squared. Good. So that's what we would have. Yeah. So now I can apply the limits, and you may say, well, if I apply the limit in the denominator, I still have square root of -1. Yes. What did we do? Did we solve the problem? Well, this could be complex, I don't care. It could be imaginary. But what happens when I apply that -1 to t? It becomes -1 squared minus 1 divided by square root of -1 plus 1 squared. Yes? This is some number. I'm not worried about it for the time being. But what is -1 squared? 1. So 1 minus 1 divided by whatever mess that is. Right? What is 1 minus 1? That's an easy question. 0. So I have 0 by whatever number this would result in. Right? Yes.
How do you get t squared?
Isn't it just?
Oh, not way too excited. Oh. Take that back. I could try. So square root of t squared is just t. It didn't work the way I wanted to. Oh well. So that would become -2 divided by whatever mess that is. If it went the way I wanted to, that limit would have been 0 easily. But this is -2. And that would be some number. It's going to be imaginary. At the end of the day, the answer is not going to be 0. It will be imaginary, right? So in this problem, even though we applied that trick, we're not going to get a real number value as a limit, yes.
Why would it have been 0 if it would have worked out the way you wanted it to? Like, why would it equal 0?
If it worked out the way like I wanted to, it would have been 0 divided by square root of -1 plus 1 squared. Yes, and that is some number, some complex number. So 0 divided by any number is 0, right? So life would have been easy. That's what I envisioned by broken things. So in this case, the limit is d. Do we see the difference? So if things worked out really well, I would have had 0 here, imaginary or not, as long as the denominator doesn't become 0, I'm fine. In this case, it's an imaginary number, it's not going to become 0. So, but it will be imaginary, so we will not have a real number value as a limit. So the point I want to make is to use that trick, which is conjugate or conjugation. That's what Geo said as fractionalization. Okay, so at least maybe you got the idea by relating it to the previous part or previous problem. So since I see a radical and I know that I can't apply the limits directly, 0 over 0 is what we call an indeterminate form. So we have to do something. So going to use the same trick that I used back there. Quite a few people got it right, so we have to multiply and divide by the conjugate. What is the conjugate of that term?
Plus square root of 2 minus 2.
Good. So I can't just throw in that term like I want to, but if I did multiply and divide by the conjugate, then algebraically I didn't do anything wrong. Yes. Now, if you look at these two terms, I call that A, that's B, A, B. What I have is A minus B times A plus B. From the last problem, what is A minus B times A plus B? Plus minus. So A squared, square root of t, 2 plus t squared, minus square root of 2 minus t squared. Yes. A squared minus 3 squared divided by 2 times square root of 2 plus t plus square root of 2 minus t. Oftentimes, I have seen students plug in the limit at this step. But if you do it at this step, you end up getting the same answer, 0/0, right? So be patient and see what happens to the numerator. So the root and the square will get cancelled. Yes? The root and the square will get cancelled. Divided by t, square root of 2 plus t plus square root of 2 minus t. Good. Distribute that negative. 2 plus t minus t, minus of minus t is plus t, divided by 2, square root of 2 plus t, plus square root of 2 minus t. Good. So 2 and minus 2 will get cancelled. T plus t is 2t. Running out of space. I'll just pull this up so that you can see. I just wrote limit t approaches 0, 2t divided by t multiplied by 10. Again, I've seen students apply the limit right at the step and end up at 0/0. So don't do that. If you observe the expression, there is a 2 in the numerator, t in the numerator, t in the denominator. What would happen to the 2 t's? Will get cancelled. And that's what we will have, yes? With this limit, we know if you have function over function, we can apply the limit separately. Limit t approaches 0 of 2 is 2, because there is no t. Would that function cause a problem at t equals 0? No. So as t approaches 0, the only thing that's going to happen to that is it will turn into square root of 2 plus 0. It's a proper function. Would that function cause an issue if t approaches 0? No. It'll just end up being square root of 2 minus 0. Yes.
So earlier in the whole process, where it was parentheses 2 plus t minus parentheses 2 minus t, how did it become 2 plus t minus 2 plus t?
Square root of 2 plus t squared. You get cancelled, same.
Okay.
Now, the denominator is 2 over root 2 plus root 2. Yes, which would be 2 over 2 root 2. What happens to the 2's? They'll get cancelled. So the answer is 1 over square root of 2. Good.
How did you get the 2?
Leslie? No. What seemed quite impossible at the beginning actually had a limit. So this is what I recommend you to do. You know, me, I have lots of experience, so I see something like that immediately, you know, the gears start turning. But if you encounter something like this, the first thing I want you to do is graph. Okay, take this part and graph. If at 0, there isn't a break, and if it smoothly crosses over, then there is a limit, nothing will form. So your answer cannot be 0 or 0. So I want you to graph this, on the graph. It will cross the axis, y-axis at one of the slides. Go ahead.
So when you have the rad 2 plus rad 2, how do you get to rad 2?
Apple plus apple.
So you wouldn't have the square root of it.
If you multiply it. So it's square root of 2 times square root of 2 would be square root of 2 times 2. Do we agree? That's square root of 4. What I'm doing is I'm adding them. So what I'm doing there is square root of 2 plus square root of 2.
You got 2 square root 2.
So I have 2 of them. If you think of this as, hot dog, one hot dog, another hot dog, how many hot dogs do you have? 2 hot dogs. Again, one size. So you don't think